Hello all, this is going to be a review of the key concept of Chapter 3. So recall that a relation is just a set of ordered pairs that can be written as an equation. Remember that a set is written using brackets, and that the ordered pairs within the brackets, which are the relation, will have a pattern that can be written as an equation. There are several different ways we can write out relations. There is a list of all of the ordered pairs within the relation. You can write that list as a table. You can also write it as a map where the oval on the left represents the domain or all the x values, and the bubble on the right represents the range or all the y values. You can also graph relations, and finally you can always have an equation that represents the pattern you see in the relation. And you will need to know how to do all of these on your test. So this is something that we did not talk about the first time we went over this lesson. And this you can consider the secret thing. We are going to learn about inverse relations. So inverse relations sound a lot more complicated than they are. If we had an ordered pair A, B, that would be the relation. The inverse would just be B, A. So not too complicated. So for example, here we have 0, 2, and negative 5, 4 as our relation. Therefore, the inverse would just be flip-flopping these, so you have 2, 0, and flip-flopping these, so you have 4, negative 5. And you can see with this example here how simple it would be to map that. Go ahead and take a second to read over that, and then try this example on your own. So remember that we have to identify functions, and that functions are just a special type of relation. They're a relation in which each element of the domain is paired with exactly one element of the range. In other words, for every input, there is exactly one output. Just remember that every equation is a relation, that only some relations are function, and that, most importantly, every input has exactly one output. And if we're looking at graphs, we can use the vertical line test to determine whether something's a function. So if I had a vertical line crossing anywhere along that parabola, it would only hit one point at any given moment. Whereas if I had a vertical line passing through this sideways parabola, it would hit 2 points, meaning that this input has 2 outputs and therefore does not follow that rule. So it is not a function. So when we talk about function notation, what we're talking about is writing things using f of x, which just means the function of x. And f of x is just another way to write y, because it's our function of x, which is our output. Y is just our output, therefore they are the same thing. So if I was given this equation, to write it in function notation, I would simply replace the y with f of x. So if I were to look at this first example, or rather the second example, example 2, I have b of 5. So even though it's a b and not an f, we're still talking about a function of 5. So since it says b of x, or the function of x, is 6x minus 8, and they want to know what b of 5 is, all I have to do is plug 5 in for x, because I'm just looking for what the function of 5 is in this case. So I'll have 30 minus 8, which is just 22. Which means that my function of 5 is 22. So go ahead and try example 3 on your own. In the next section, we're just going to talk about linear and nonlinear functions. Remember that a linear function is just a straight line with no bumps or curves or anything. A nonlinear function is just everything else that is not a straight line. So linear functions can be written in standard form, which is ax plus by equals c, where a, b, and c are integers. So if we needed to determine whether something was linear based on the equation, we can see here that when we have ax plus by equals c, that we have a single x, as in not x squared, and a single y, and that all of our coefficients are integers. So looking at this problem, if I can rearrange it such that it is in this form, ax plus by equals c, then it is indeed a linear equation because it will be in standard form. I can rearrange that by adding 2x to both sides, which means I'll have positive 2x plus y equals 5. And because that's in standard form, it is indeed a linear equation. Now if we look at b, we have 2xy minus 5y equals 6. So the issue here is that that has another y attached to it. There is no way for me to rearrange it to put it into standard form because I couldn't divide by y on everything or else I would get rid of this y as well. Therefore, it's not a linear equation. So looking at these two, take a moment to try to decide whether or not they are linear or nonlinear. If you said that this first one was linear, you would be correct, because I could rearrange that and put it into standard form. And this is how I could do that. Since I have 1/3 y equals -1, first of all, I could multiply everything by 3 so I don't have fractions. So that would mean I'd have y equals -3. But now you're probably saying, well, we don't have our ax. Well, really, we do have our ax because we have 0x plus y, which is just 0 plus y. The reason that we know that this is going to be linear is because if I were to graph y equals -3, I would just go to -3 on my y-axis, and I would have a horizontal line. And because that's a straight line, it's linear. Therefore, this is a linear function. However, if we were to look at this next example, we have x squared. There's no way for me to rearrange this so that it would be in the form ax plus by equals c. The most I could do is get -x squared plus y equals 3, but I still have that x squared. If I were to square root everything, I would then get the square root of y, which would still not be in standard form. Therefore, this is not a linear equation. So recall that anytime I have a line, the point at which the line intersects the y-axis is my y-intercept, and that will happen anytime x is equal to 0. Similarly, where the point at which the line intersects the x-axis is the x-intercept, which is where y equals 0. Something that we did not talk about in the last lesson were zeros. Zeros are the points at which f of x is 0. And the 0 of a function is the same as the x-intercept. Sometimes you'll have multiple zeros later on in these chapters, but for now, most of the time you'll just have one. So for example, if I had f of x equals 2x plus 1, the way I would solve for the y and x-intercept is like so. So I know that the y-intercept is at x equals 0. Therefore, I'm just going to plug 0 in for x, so I'll have 2 times 0 plus 1, which would be 0 plus 1, which is 1. Meaning my y-intercept is 1. So if I were to graph that, I would just go to 1 on my y. To find my x-intercept, that would be at y equals 0. But remember that y and f of x are the same thing. So I'm just saying that f of x equals 0, so 0 is 2x plus 1. Solve for x. Therefore, x would be -1/2, so my x-intercept would be at -1/2, and that would be my line. Now, so if I'm looking for zeros, I know that my 0 is the same as my x-intercept, therefore my 0 is right there, and that is at the point -1/2, 0. So that is the 0 of my function. So remember to change something into standard form. First of all, we know that standard form is ax plus by equals c. And all you would have to do here on this first example is rearrange it such that the x's and the y's are on one side. So I have negative 2/3 x plus y equals 5. Now this is fine except that negative 2/3 is not an integer. So what I'm going to do is look at all of my fractions in the entire equation. I only have 2/3 in this, or negative 2/3 in this case, and multiply the entire thing by the common denominator, which in this case would just be 3. So I want to multiply everything by 3, which in this case would just cancel out for the x, so I'd have negative 2x plus 3y equals 15, and now my equation is in standard form. So try this next one on your own. To graph a standard form equation, all I need to do is find my x and y intercept. So remember that my x-intercept is at y equals 0, which means that in this case, it'll be negative x plus 0 equals negative 5, which means that x is just 5. So I just go to 5 on my x for my x-intercept. For my y-intercept, that's at x equals 0, which means that I would have negative 0, which is 0, plus y equals negative 5. So y equals negative 5 is my y-intercept. So I'll just graph that there. And then I connect those two dots and I have my graph. So try this next example on your own. So recall that when we're dealing with arithmetic sequences that we should use this formula where a sub n is the nth term, a is the first term, n is the position, and d is the common difference. So if we were to look at this example, we have 2, 6, 10, 14, 18, ... So we know right away that a is our first term, so a is equal to 2. We also can see that to get from the first term to the second term we add 4, to get from the second term to the third term we add 4, and so forth. So our common difference is going to be 4. So since we know that our formula for any given arithmetic sequence's nth term is a sub n equals a plus n minus 1 times d, and we know that the a sub n and the n are going to just stay variables, we have all the information we need to figure out an equation for the sequence. So what I'll do is say, okay, a sub n equals 2, because that's my first term, plus n minus 1 times d, which is my common difference, which is 4 in this case, and I just have to simplify my expression on this side. The way I would do that is go ahead and distribute that 4, so I'd get 2 plus 4n minus 4, combine my like terms, which is 2 minus 4, so I'll get 4n minus 2. So that means that my formula for this sequence will be a sub n equals 4n minus 2. That will allow us to figure out any term in the sequence. So let's say I wanted to find out the 100th term. That means I want a sub 100, and I just plug in 100 for n, so I'd have 4 times 100 minus 2, which would be 400 minus 2, which would just be 398, which would mean that a sub 100 would be 398. So if I wanted to figure out this sequence right here, I would say, okay, the first term, a, is going to be 8. The common difference is 6 between each term in the sequence. Therefore, my formula will be a sub n equals 8 plus n minus 1 times 6, which means I'll have 8 plus 6n minus 6, which will just be 6n plus 2 when I combine my like terms. So a sub n would be 6n plus 2. So that goes here. Try the next few on your own. See if you can get them. For this final page, we'll have situations where we know one term in the sequence and we know the common difference in the sequence, but we don't know anything else. So let's take a look at this example down here. We know that our fifth term, or a sub 5, is equal to 14, and our common difference is 3. So we have some different information for our equation. We know that a sub 5 is equal to 14, which means that when n is equal to 5, a sub n is equal to 14. We know that our difference is 3. So we actually have enough to figure out what the nth term equation would be for any term in this sequence by plugging in 3 out of the 4 terms in the equation. So if we know that a sub n is equal to a plus n minus 1 times d, we actually have everything for this equation except a, which is the only part that we need in order to find an equation for this entire sequence. So what I'm going to do is plug in what I know. I know that when n is 5, the equation is equal to 14. So I'll say a, the one thing I don't know, plus n, which is 5, minus 1, times d, which is my common difference, is all equal to 14. Meaning 14 equals a plus 4 times 3. So 14 equals a plus 12, which would just mean that a equals 2. So now that I have my a and my d, I can go back and say, okay, my a for this equation is 2, my d is already given to me, which is 3, which means a sub n is equal to 2 plus n minus 1 times 3. So I have 2 plus 3n minus 3, which is just 3n minus 1. So go ahead and try these last 3 on your own, and that's it for the Chapter 3 review.